Hello, everyone. My name is Omer Yaari, and this is Dean Bracha. We are senior backend engineers at Autodesk, and welcome to our presentation, The Hunt for the Lost Bytes. Let's start with a story. It was a regular Tuesday morning. Coffee was hot. CI/CD was green. Life was good. We finally had time to start working on all the things that we didn't have time for. And then suddenly, our phones started vibrating. Pager duties, Slack, email. Even our smart fridge started pinging us. And then it happened. The manager called. You know it's serious when they use voice instead of Slack.
He said, hey, what's going on? The application is down, users are unable to log in. What's going on? And then we looked at the application. It looked like it needed both a reboot and a therapist. Meanwhile, our stock price started decreasing, just like our confidence during a live demo. Then finance pinged us, asking if we accidentally created a market crash. And then the CEO called. He only said one line, fix this now. We looked at each other, only two words in our mind, memory leak.
So what is a memory leak? A memory leak is like stuffing junk in the closet until it won't close. Basically, it's a memory that is no longer needed and is not released. For example, variables left in the global scope, event listeners that we forgot to remove, and misconfigured third-party libraries. But why do we care? Well, it has a business impact. Users are unable to use the product, users experience slow performance, and unstable scaling happens, and eventually it can lead to a high cost. And this is an example for a memory leak causing code. So here we have an array, a global array. We have this interval, and we have this function. Every time this function will execute, a new string will be added to the array, and this function will execute every 1 second. And as you can see, this array is going to grow forever until the app will crash due to memory leak.
So, what do we see now? We see 3 deployments, right? We also see the first load of the application. We see on the first deployment, we see a 5% of increase of memory. But on the second and the third, we see an increase of about 15%. In this one, you see the memory increase of the failure of the problematic deployment. But you see it on both problematic deployments, right? So we definitely have a memory leak. And every now and then, we see a release of memory leak. We see the release of the memory. We have a guess about why this happened. We are guessing that the autoscale component of Amazon identified the memory leak, and then it rebooted and inserted new instances. So we have a leak. What should we do now?
So we first thought if we can revert the code. Well, reverting isn't always easy. Sometimes you have database schema changes that prevent you from reverting because you have a new schema in the database. Sometimes you have new event handlers that go live and you don't want to miss the events. You have infrastructure updates that you obviously don't want to roll back to. And sometimes it takes multiple deploys until you actually figure out that you have a memory leak. And it's nearly impossible to find the right commit to revert to. So the second thing we tried is to correlate the memory leak to a specific endpoint or a specific request. In this example, we use New Relic to monitor our service. And unfortunately, we couldn't find the cause or any anomaly. We also tried to reproduce it locally, but memory leaks are hard to reproduce locally. mainly because there's no real traffic in local environments, and these memory leaks are often triggered by edge cases. We also tried to look at previous commits and ask our teammates if they know anything, but we didn't find anything.
So how do we actually find these little bastards? We have a couple of memory tools to get this going on. We have monitoring tools. Most of you know this by APMs. You have Datadog, you have New Relic, Dynatrace. We have profiling tools. We have Node.js Inspect, which is the default inspection tool for Node.js. And then we have Clinic.js. Which is an external tool. We also have the possibility to have if snapshots. This is also called if dumps in different languages. So let's begin exploring these tools. For the monitoring tools, we have, for example, New Relic. New Relic allows us to do a lot of things. It allows us to see the different web transactions. It allows us to see error inbox, the top performing SQLs. But it has advantages and disadvantages. These are some of the advantages. So we have the possibility to have early detection. We can set the result, we can set alerts, and then we can combine them. We can decide to have a warning or a critical alert when a memory is rising or a CPU is rising. And then in the monitoring tools, we can also see patterns. If we look for a specific day, if we look for a specific hour, we can see what's going on exactly. But we also have a low overhead. So this is something that is really good. It means that it's production ready. It means that the monitoring tools doesn't take a lot of resources from our system, so we can use them in production. It also has some problems. It doesn't state exactly what is the root cause. Okay? It only states that the memory is rising, but it doesn't state the why. And sometimes it also has a false positives. So a memory that is rising doesn't necessarily mean that there is a memory leak. This is the other tools that we have. We have a profiling tool. So for profiling tool, you can see in here, this is Clinic.js, and this is something called the flame chart. Flame chart basically states that the most used function will show in the darker red, okay? So it basically states which function will allocate most of the memory. This also has some advantages. Basically, it tells us exactly what's going on in the system. You can see the exact memory and the CPU that is being allocated. It also allows you to find hotspots, as we saw in the flame chart. It tells you exactly what is allocating it. But it has a lot of disadvantages. One of the main disadvantages is having a performance hit. So when you install a profiling tool, it basically takes about 5 to 20% of your resources from the system. This basically means that you can't use it in production because it would probably create a lot of and increase your cost. And another disadvantage is having a data overload. By having this tool, you have a lot of information. It's really easy to being misled to which information to actually read. For the last tool, we have if snapshots. An if snapshot is a snapshot of the memory in the specific time that you have taken it. You have the possibility to see the shallow size and retained size. We'll talk about it later. And when you load the memory, you see exactly what's taking the memory. Let's take a look a bit about the advantages. The main advantage is it tells you exactly what was the problem. And not only that, you can also compare snapshots. So if we'll take the before the memory leak started, and then we'll take the afterward, so 2 snapshots, and we'll compare them, we'll be able to see exactly which variables the growth in memory. But it has some disadvantages. It's extremely manual and slow, meaning that we need to take the snapshot by ourselves. And by slow, it means that you can't use it in production so easily. Because when you take the snapshot, there is a pause of the application, and then the application comes back. So it's not ready for production. And the final disadvantage is that the timing of the snapshot really matters. If we take it, for example, in the wrong time, it means that we'll have pretty much a useless data. So how do we choose which solution to pick? Basically, by what's immediately available. So for us, we actually choose monitoring tools because this was available for us. And we also choose heap snapshot, which was extremely easy to implement.
So let's deep dive into the investigation. So what we basically did, we wanted to generate a heap snapshot in our web server. So we added a special route that basically generates a heap snapshot and uploads it to S3 so that we can download it later. So as you can see here, this is a pseudocode representation of the actual function. We also added a feature flag so that we can control whether this endpoint works or not, because every time you generate a heap snapshot, the main thread is freezing, so you don't want to do it during peak hours or do it too many times. This is a function that generates a heap snapshot. It's a very simple implementation. We basically need to use the V8 API. And here we uploaded the snapshot to S3. We also returned the heap snapshot to the function that called this function so that we can log the name of the heap snapshot and so that we can see and know which file we uploaded to S3. So this is basically how it looks when you load the heap snapshot into the Chrome memory tab. You see a lot of strange things. It was very overwhelming for us at the start. For example, you see compiled code and the code that's in strings, and it's actually a normal behavior. So you would see it a lot. We also need to talk about shallow size and return size. These are two terms that are used when you investigate memory leaks. You can see it in here. It's shallow size and return size. So basically, shallow size is the memory of the object itself takes the hold. And for example, if object A takes 2 bytes, then the shallow size of object A would be 2 bytes. Return size is the sum of memory of the object and all other objects it references. So here's a nice example. In this example, the shallow size of the object A is 1 megabyte. But the return size of object A is 5 megabytes because it references all these objects, and they can't be released unless A is released. So we tried looking at the heap snapshot, and we found something interesting. We found an array. You can see an array here that takes a return size of 23% or 32 megabytes. And you see these query sample objects and query trace aggregator. So at first it looked like the memory leak, but actually it's related to New Relic, and we used New Relic, and we had some feature enabled in production, and it wasn't the actual memory leak cause. And we kept looking at the heap snapshot, and eventually we found a clue. We found an object that has a return size of 15% or 23 megabytes. And it looked kind of weird. Ready error connect. It looks like some kind of a client. So once we clicked on it, on the object itself, and every time you click on an object, you have another list here. We couldn't really display it here because it's too long, but you have another list of retainers objects, and these are the objects that prevent the object you're clicking on from releasing. So this is the returners list of that object that we saw before, and we saw Redis client, Redis cache. We also saw loads of Redis cache, 18,000 of them. And it actually was familiar because we worked on this particular code and we recognized it. And it actually led us to the cause. So the memory leak in the code, the actual cause was because of this class. It's a class called cache helper. We use it to cache requests to other services inside the Autodesk network. And every time this class is instantiated, this function is called. We use Node Cache Manager, and in order to use Node Cache Manager, you have to provide a store. So this function was called, and eventually it also instantiated this class, this store. This store does many things. It instantiates a new Redis client. It also registers events to the event emitter, but it never released these events. So basically, it added up because this cache was used not in every request, but in a lot of requests. And eventually, it took a lot of memory until the app crashed. So in order to fix that, we chose to make this cache field inside the cache helper to make it a singleton. So every time it gets instantiated, it will only instantiate the Node Cache Manager once. And the store class that we saw earlier will only be instantiated once. So this is the result. I'm not sure if you can see anything. But here you can see the line. You see, way much? Can't. Okay. So imagine this is a line, a huge memory increase of previous deployment. There was a line here, and then after the fix, this was the line. It's you see a slight increase in here. It basically means the first load of the app, but after that, it was relatively flat. So this was the actual memory leak, and we actually solved it.
So looking back at the retrospective, we basically want we are an enterprise, right? Either we're an enterprise or a startup. We want to make sure that this won't happen in the future. So we decided to have a couple of things. We decided to improve our production detection. So we improved the alert result, whether we added more warnings, more alerts, but we also wanted to have preventative actions. So what preventative actions can we take? We can actually add stress testing in the local environment. And we can also add a bigger and higher frequency of deployments, right? For the other part, we decided to add more documentation. We added a wiki that explains exactly how to investigate the situation. And we decided that this would be a good understanding, to have a better best practices, right? So we found 3 best practices. This one is actually simple. We need to limit our objects' lifetime. So we need to avoid global variables. We need to scope the variables more tightly. We need to scope them to the specific location, whether it's a function or a class. And we need to nullify the references when we are done. And we also found out that most of the problems are actually occurring when we have event listeners and intervals. There are other reasons to memory leaks, but these are usually forgotten. For the second part, we understood that we need to monitor our memory more frequently. We understood that most of the times, memory leaks are happening when we have deployments. So when we have deployments, we are going to take a look at the monitoring tools and try to see for the next hour, can we see any increase of memory leak? Can we see any pattern that we didn't see in previous deployments? And for the third part, as I said, we need to have more frequent deployments. If we'll have more frequent deployments, we can easily pinpoint the problematic commits, but it also means that we have incremental changes. so it will be extremely easier to roll back. So what did we learn from this? We learned that memory leaks are extremely invasive. They also demand our immediate attention. We need to understand that we need to have infrastructure that supports us. So if we have the monitoring tools that supports us, it will be extremely easy to investigate the problem. And what we understood is that we now know how to investigate the memory leaks and how to proactively protect ourselves by using the 3 practices that we had. Any questions?
Thank you, everyone.